Welcome back. So for those of you interested in diving down into the real kind of nitty-gritty of AI, our tech talks are for you. So the first talk is from Adrien Gaidon, who is the machine learning lead at Toyota Research Institute. And he's going to be talking on the subject of driving the machine learning autonomy. Adrien is actually working on an open research problem, or a series of open research problems, in world-scale learning for automated driving, and especially on self-supervised learning and other techniques that go beyond supervised learning. He received his PhD from the Microsoft Research Institute and has over a decade of experience in academic and industrial computer vision. So, over to you, Adrien.
Hi, everyone. It's a pleasure to be here. I'm Adrien Gaidon, and I lead the machine learning research team at the Toyota Research Institute. It's my pleasure to talk about how we're scaling up machine learning for autonomy in my team. So we are doing machine learning research around a variety of topics across the full stack, sensory motor stack for robots and cars. And that includes scene understanding, self-supervised learning, simulation and auto-labeling, but also behavior modeling and prediction, learning for planning and control. And that's a lot of the research that we're publishing in the open. You can find a lot of our papers online if you're interested. I'm going to give you a brief summary of what we've been up to. So one of the core challenges for scaling up machine learning models, in particular for perception, is how do you get supervision? And to tackle this issue, we are working on self-supervised learning. So self-supervised learning consists in optimizing machine learning models using an objective function that is directly derived from the raw data itself. In our case, we use projective geometry as a source of self-supervision to predict the dense depth of a scene from a single image. So this is like the high level picture where you see that you have an image IT that is fed to a deep network. In our case, one of our networks that we proposed and presented at CVPR last year is called PACnet, which takes again this input image and then says for every pixel how far the underlying object is. And so this depth image enables you to then use projective geometry to reconstruct, let's say, a past image if you also know how much the camera has moved between, let's say, the previous image and the current image. And so this is how we can use self-supervision. If we're not able to reconstruct properly, it's not because geometry is wrong, it's because our network parameters are incorrect, and we can optimize them to minimize that reconstruction error. So here you see basically the underlying equation that we are able to leverage, and you see the estimated parameters t hat and d hat, which are these transformation of the camera motion from previous frame to current frame, and also the depth, which is really what we want to predict as a task, how far things are. And this is really the source of self-supervision. It's really just the geometric equation. And what you can get is now you can see that you can learn a neural network that takes as input the image you see on the upper left and can output the color-coded depth map that you see on the bottom left. And because you know the camera parameters, you can basically reconstruct a 3D point cloud and really understand the full 3D world around you. One thing that we've done very recently is to extend this to not just what you see in this front camera, but what you see all around the car. And that's what we call full surround monocular depth. And so it's very much an extension of the ideas that I presented before, but we're also leveraging the relationship between the different cameras that are all around in the car and looking all around the scene. Of course, in practice, you are never, like in a situation where you can never have some form of supervision. And so we also explored other avenues of extending self-supervised learning to just scalable forms of supervision. And so first, it's actually really common to have some part of your data labeled, for instance, the active learning. And so the question is, what do you do with the rest of the data that you have, but it's not labeled? And that's the semi-supervised learning problem, which is how do you leverage partially labeled data? So it decomposes naturally in self plus fully supervised for us, because in our case, the self-supervision enables learning the task directly. So for instance, predicting the depth of the image. And so we can just simply combine the objectives, the self-supervised and the supervised objectives, with some adaptation to the loss functions or the architecture. And it's not just during training, but it is also during inference. For instance, we have recently done some work where we can leverage, like partial depth information that we might get from some LiDAR sensor or some other range sensor, but that's only going to be partially working or partially covering the scene. And so we can really be have a flexible system with respect to the different sensory inputs we get. So that's semi-supervised learning. We've also excitingly moved forward with an approach that is based on differentiable rendering to automatically label the 3D bounding box of objects. And that can be later used for training 3D object detectors, including from just again, camera images alone. And in a nutshell, the idea of our recent CVPR and work that you're seeing here and the follow-up ACC work that we've done, it consists in feeding an image to a deep network, outputting scene parameters that can be then used to re-render the image. And that's typically an approach called inverse graphics. You're inverting the rendering process so that you can, with a network, and then you can re-render it with a renderer and compare the results. And so using a differentiable renderer enables you to use these reconstruction losses to really drive the learning in a self-supervised way. And after training, you can use the predicted scene parameters, the things you feed, like the network outputs and that you feed it to the renderer. Well, these scene parameters actually can be used as labels, for instance, bounding box labels. And finally, a promising avenue to get scalable supervision is obviously simulation. But this comes generally at the cost of a domain gap that might hurt generalization performance, depending on how good your simulator is. And so overcoming this gap is called solving the sim to real transfer problem, which is a specific instance of unsupervised domain adaptation. So we made significant progress in that area, including by leveraging self-supervised learning to help align feature distributions between virtual worlds and the real world. And this, for instance, an example of what you're seeing here is we can learn both depth information and semantic segmentation information in a network, but without ever having used any real-world labels, only having seen synthetic labels. And that's the example you see here from our latest paper called GUDA for geometric unsupervised domain adaptation. So in fact, like this idea of that self-supervised learning can be used when you have a little bit of supervision is kind of a general principle that we've really relied on, which is that if you're never fully unlabeled in practice, but nonetheless, self-supervised learning is the key to unlock the use of insufficient supervision. So perception is obviously a big part, and I think like being very robust to the long tail is a big challenge in perception. But some of the more exciting challenges that are being really investigated actively in the team is, for instance, prediction. So you understand the world around you, which is what perception does, but prediction is about predicting the future, and in particular, predicting what might happen, but you're not really sure. So at the core of prediction is the problem of randomness or stochasticity. And so uncertainty, how you represent uncertainty, and how do you communicate uncertainty or consume it from perception and pass it down to, let's say, a planning and control stack, this is really key. And so we've done a lot of work actually on this recently, including in collaboration with our friends at Stanford, where we're really looking at this question of how do I learn by imitation? How do I learn from how people moved, how I've seen people move in the past, but also how do we represent what is possible, what is plausible, what might happen, and how do we leverage those distributions, like really we're outputting probabilities and distributions, and how we leverage that for safe planning. And that brings me to the last part of the stack, right? We've seen perception, we've seen prediction, but it's great, but that's all passive, right? Eventually, you need to act. And so one of the core challenges, as I mentioned, is how do you act safely? And to address those challenges, we recently worked on how do we close this perception control gap using robust, risk-sensitive, stochastic optimal control techniques. And so one of the main novelty of the work, and this is a lot of, again, joint work with our friends at Stanford, is how do we model risk? How do we make decisions in the face of uncertainty where you can never be sure of what's going to happen? And so modeling risk is really essential. And one of the interesting ways to model risk is using optimization frameworks that leverage computational notions of risk. In particular, we've been using entropic risk, and which is basically the formula you're seeing here. But the high-level picture is basically like you have an environment that's stochastic, and you can model this environment and the possible futures that might happen using what I've just described before, which are these probabilistic models of human motion, of multi-agent interactions. And then you can pass in those distributions or those samples over the possible futures down to a model-based planning and control stack, which is going to optimize for a cost, like to reach your goal and avoid collisions, like optimize for safety, but at the same time doing it so in a risk-aware way using this notion of entropic risk. And what you see here is that we're able to really model, like it's a robot in blue that moves around agents that you're not too sure what they're going to do. And you see like the multiple trajectories that they could take. And the robot is able to dynamically react and adjust its behavior to go where it wants to go, but at the same time avoid any issues, do it so safely. We've also recently extended this in our paper called Rat ILQR to scenarios where you're not even sure that your model about uncertainty is correct. You're outputting a model of the uncertainty, but you need to be robust to that model not being exactly the true representation of the distribution. And this is where distributional robustness in control is actually a very important research area also for us. So in conclusion, I've overviewed really briefly 3 different core areas of our research. The first one is perception, and in particular, how do we achieve robustness by leveraging data. I talked all about self-supervised learning. I didn't talk too much about like other aspects that are really important for us, which is redundancy and efficiency. And we have a lot of papers on this. They're all available online. You can find them also on my website. So just please feel free to just reach out if you have any questions. Of course, understanding the world around you is important, but you also need to think ahead, right? And think what might happen. So this is the area of prediction, which is rendered really hard because of the stochasticity of the environment. And so I talked a lot about the uncertainty side, but what's also really important is to understand the intent of the agents and also the multiple plausible futures that could happen, so the contingency. And so we've done some work on that I've also described very briefly around trajectory forecasting and multi-agent interactions. And finally, it all needs to be used to make decisions and to make actions. And this is where I've mentioned in the area of risk-aware planning, where we look a lot at safety with risk-sensitive control, distributional robustness. Also, imitation is really important. And finally, like causality and especially counterfactual analysis are really important for us. And so to conclude, we have a lot of code available for all of these papers. We have dataset releases, especially the DDAT dataset that we're organizing the competition this year at CVPR. And it started now, actually. So if you want to participate, feel free to check this out. And you can find more on TRI's website and my website. Of course, thanks to a lot of collaborators, like it would not be possible to do without all these people. So thanks to them. And thank you again for inviting me here to give a talk. Thank you.
Thanks, Adrien.